All right. So back from so previously we talked about the six assumptions. We already know that the model is linear. Well, we at least the model that we specified is linear in parameters. We'll assume that the second condition is met. We'll assume that it is a reasonable random sample, and there are no other independent variables. There are no other explanatory variables. We're only looking at the square foot or at the square feet of the home. So there's nothing to really be collinear with it. Um, so let's look at 4, 5, and 6. So let's run a regression. So we're going to use stats models and ordinary least squares to run a regression of close price onto the square foot total. So we'll do y equal to b close price. What's the close price? We'll say x is going to be equal to our square foot total. Now we'll run a regression. Regression is going to be equal to stats models dot ordinary least squares. And our endogenous variable is going to be y. Our exogenous is going to be x, but we have to, don't forget to do the add constant. You have to add the constant for the exogenous because you have to have that column of ones. You have to have the column of ones in order to get the constant. And then we'll print our regression summary. Now we can see it. So this is linear in parameters. So assuming that it's a good model, it is linear in parameters. There is no collinearity because we only have one explanatory variable. So let's look at the residuals. The mean residual has to be 0. If it's not 0, then there'd be a problem. You can see this is pretty close. You can use Seaborn. You can use Seaborn to do a distribution plot, and you can see it. It should be mostly normal. If it's normal, then that's a good sign. So it does look like a normal distribution, and it's centered at 0. So that's a good sign. You can see that it does seem to have a maybe not fat tails, but it does have some large residual on both sides of it. So that's not necessarily a good thing, but it is relatively normal. So that's good. So now let's look at the fifth assumption. So the fifth assumption is that the variance of the error term given the explanatory variables is constant. So this means it's a constant variance. So what this should look like is, say we look at, over here is our residuals. Maybe this is our x, or our square foot, and it should be pretty constant. So maybe the variance should be something like it should be within some bounds. But if it's non-constant, then maybe it would look kind of like a cone. So it's heteroscedastic. So hetero would mean that it's not the same. Homoscedastic, constant variance. Constant variance should be within some bounds, and it should be relatively constant. If it's not constant, then it may look like a cone. So this would be a bad thing. If it looks like a cone, then it may violate, or it would violate, the assumption. There's ways around that if it does, and there's ways to test for that more accurately, but given the current environment, we didn't necessarily have time to cover all of that. Anyway, so let's do a regression. Let's look at a scatter plot. So we'll look at a scatter plot. We'll set x to be our square footage, and the y will be the residuals. We'll look at this, and you can see the cone. You can see the cone pretty clearly. It has a very conal shape. So this would mean, or be a good indicator, or good indication, that there is a non-constant variance. So this would violate our fifth assumption. So to test for this, there's hypothesis tests about this. You set up hypothesis tests and say that the no is that there is a constant variance. Alternative would mean that there isn't. Then you do a test to test for the significance of that. But without getting into all of that, one way that does sometimes fix it is if we switch it to a log model or a double log. So we take the natural log of our y. So we do the log of our price, of our closing price. And what this does is it makes some of those errors a little bit smaller, so it keeps it closer within our bounds. So this is one easy way that will sometimes fix the problem of a non-constant variance. So we'll run a new regression using stats models, ordinary least squares. We got our y. We have our exogenous. Don't forget to add a constant. We're going to fit it. Then we'll print our regression summary. So now you can see that our R squared has gone down, but it is still statistically significant. All of this is still significant. And if we plot our new residuals, maybe now it is less. So we can see that now the shape still isn't ideal. It's still not ideal, but let's plot our x and our reg dot predict. Let's see what this looks like. So here is our predicted line. There you go. So this makes a little bit more sense. Okay, so this is what our new regression looks like. So we have our data. This is log price at the home. This is log square feet. We look at our line. Let's do reg dot predict. So we'll create the line over top of it. So now you can see where that non-constant variance is, or maybe it's not non-constant variance. Maybe it's autocorrelation. Maybe the error terms are correlated with previous error terms, or maybe there's a problem there. But so this is our new regression model, and the new specification of this regression. So it's a little bit better, but not where it needs to be. We're still not there. We still can't use this to predict anything. But our new specification, the new specification is now we're looking at log price. So the natural log of price I is equal to beta 0, beta 1 times the natural log of square foot I plus our error term. So this is the new specification for the regression. So this is our new regression model. This is our new regression model. And if we want to estimate price, so whenever we plug something into this, if we plug in log square feet, we don't get price out of this regression or out of this model. We're getting log price. So if you want price, you have to do e to the power of both sides. So e to the power of both sides would get rid of that, and e to all of that. So this would be equal to price. Price would then be equal to e to the power of beta 0 plus beta 1 times the log of square feet plus our error term. Excuse me. So this is our new specification for the regression, and you can see that it's still not, we still didn't eliminate our problem, but now we have potential more problem with autocorrelation. So we'll cover that in the next video. We'll cover that in the next video, but for now, notice that there is heteroscedasticity. This is a non-constant variance, and if you just do price with respect to square feet, you do not have a good model. So even though, judging by all the statistics, it still looks like it would be a good model going forward, and maybe it would have predictive power. If you were to use this and use square feet alone, it would not give you a good estimate for what the price should be.